Okay, so we are in remote session number 2. Today is January 26th, and our plan is to cover 2.2 and 2.3. So last time we talked about solving equations in one variable, and we also talked about linear equations and rational equations and how they're different, right? Fundamentally different because we could have division by zero in rational equations when it's not the case for linear equations. So the second part of this section is talking more about lines, different forms of linear equations, and one of the most important concepts for linear equations is a slope. So let's talk about slope real quick. And again, for some of you, this is a review, but I'm going to assume that not everybody has seen this material. So we're going to go through all of the details. Let's say we're in a plane and we have a line, a straight line that goes up to the right. Okay. And we want to decide what the slope of this line is. Okay, one way to determine the slope of a line is to pick any 2 points on that line. Okay, so let's call this point A and point B. So I'm going to mark them right here, A, B. Okay, and then we can compute the slope following this formula right here. So m is equal to y2 minus y1. And graphically, what that is, it is this distance right here. Okay, it is run, right? I'm sorry, this is race. I keep switching them sometimes. So this is your rice. Okay, that's the vertical distance. Okay, and then on the bottom in the denominator, that's your x2 minus x1. That is the change in x. Okay, so that's going to be this horizontal distance right here. Okay, the slope of a line tells us a couple of things. It tells us how quickly our line changes, right? What is the rate of change? So that the language that you guys will see in calculus, rate of change, how quickly and in which direction. Okay, so now you might be asking, does it matter which order I do the coordinates? And the answer is no. You could have also written it as y1 minus y2 over x1 minus x2. Okay, as long as we're consistent in keeping those indices in order, right? So you see how my y2 and x2 match up with y1 and x1, right? So either way, it is standard to use this equation right here, but really it doesn't matter. You can pick any of those points to be the endpoint and you will get exactly the same answer. Okay, so a couple of things before we go into solving problems. We say that if our slope is positive, visually you can picture my line going up to the right. Okay, so it would have a shape like this, right? Okay, and then we can talk about steepness of the line, right? How quickly does it go up? That's when a number is big. If it's going slow, so that's your growth, right? So if it's growing linearly and slowly, that means you have a fraction, but that's a positive value. Okay. Then we could also have slope being negative. In this case, we say our line is decreasing, so it goes down to the right. Okay, again, here we can talk about steepness as well, except in this case, the value of our slope will be negative. Okay, so models would be something decreasing over time if t, your independent variable is time, right? And then what else can happen? What if m is equal to 0? So no change, right? So you can start making this connection with change. No change is happening, right, in your line. What does that mean graphically? That means the line is horizontal. Okay, and one other extreme, m is undefined. Okay, m is undefined. So this concept might take you some time to really wrap your head around. What does that mean? Doesn't exist. Okay, when you have a vertical line, okay, and you can think about it as what is the change happening here? As you move to the right, well, you don't even need to move to the right. The change is even an up and down, okay? So there is no way to define the change here because we have a vertical line. So these are all the concepts that you might have seen some of it in your algebra class. But now I want to start connecting this to the study of calculus and introducing slowly that language that you will hear. Okay. So that's your slope. This is how we compute it. Let's go ahead and solve the first problem. Find the slope of the line passing through the given points, A and B. So that's example number 3. So what is our slope here? One way to do it is just follow that formula. So that would be 9 minus 4 over 7 minus 5. So we get 5 over 2. What is that? That's 2.5, right? Okay. Or we could also compute it by saying, okay, let's just subtract coordinates of uh, B from coordinates of A. So that would be 5. Oop, no, 5 doesn't go here. Would be 4 minus 9, and then 5 minus 7. And notice what's going to happen. Yeah, you're going to get negative 5 here, but also you're going to get negative 2 here. The final answer is the same. Okay. You do not need to do it twice. I'm just emphasizing the point that it doesn't really matter which way you're going to go, as long as you're consistent. Okay. Let me pause here for a second. You guys, if you have any questions, anything you'd like to discuss before we go on into more examples, let me know. Okay, I see thumbs up. That's great. Thank you for that. Okay, so now that we know how to compute the slope, there are 3 different forms that we can use to come up with an equation of a line. Okay, so we have slope-intercept form. Slope-intercept form tells us 2 characteristics of our line. The slope right here, m, and B stands for the x-intercept. Okay. Nope, just kidding. Y-intercept, right? So if x is equal to 0, that's where we have our line crossing the y-intercept, right? So this is your y-intercept. Okay. That's one slope. That's one of the most common forms to use. This is how we usually see our equation, right? Y is equal to 3x minus 5, right? So that's one example. Okay. Then we have point slope form. And this one is used for when you know characteristics of your line, you know what the slope is, and you know any point that's on that line, and you would like to cook up a recipe, right? So come up with an equation of the line. So this is kind of like a constructive equation that we would use when we're given information about our line. And then standard form is just simplified and kind of combined terms in a form like this: ax plus by is equal to c. And this form you might not have seen, but we introduce it now because eventually we will extend this equation into an equation of a plane. Okay, and that's, so this is kind of going a little bit forward with calculus 3. We will have more than one variable, right? So this is an equation of a line in standard form. Again, not very commonly used, but it's good for you to be introduced to this terminology. Okay, so now let's go ahead and do the next set of problems where we're asked to come up with equations of lines. Problem number 4 says find the equation of the line going through this point 2, 5 with the slope 4. Okay, so I'm looking at my different types of forms, and what do I have? I have a point, so let's give it a name. So let's say this is point A, and I have a slope. Point slope, that's the second form. Okay, so let's go ahead and use that. So I'm going to do y minus the y coordinate, that's 5, is equal to 4, that's my slope, times x minus 2. Okay, so that is my equation, the setup. We shouldn't really stop here, even though it's not incorrect, but it is kind of assumed that we will simplify everything and put it into this slope intercept form. So let's go ahead and do that. This is not too complicated. We get 4x minus 8 here. So let's solve it for y to have it in that slope intercept form. This is 4x, negative 8 plus 5, right? We're going to add 5 to each side. So that's going to be minus 3. And that is your final answer. Okay? All right. 4y is equal to 4x minus 3. I'm going to go back and just kind of double check everything. The slope is 4. We can see it from the equation. Good? Okay. If I plug in 2 for x, I should get 5. 2 times 4 is 8. 8 minus 3 is 5. Okay, so everything checks out. Okay, so we're good to go. All right. Let's go ahead and take a look at the next problem. This one says find the equation of the line in standard form. So I'm going to highlight what they want from us. Standard form. Slope is negative 1/3. Okay, and we have a point 1, negative 2. Okay, let's go ahead and do this problem. I'm going to once again use this second form, point slope form. This is what we use to construct equations, right? Okay, so y minus, I'm going to be careful here because we have a negative sign, negative 2 is equal to negative 1/3, that's my slope, times x minus 1. So just to make sure we know where everything comes from, what are these? This is my y null, and this is my x null, and this quantity right here, that's my m. Okay, we're just following that formula. Okay, now what should we do here? Okay, so let me go ahead and rewrite it like this. This is y plus 2, right? Minus negative. It gives us a plus. Here I'm going to get negative 1/3 x. And what else do we get here? Negative times negative, that will give us a positive 1/3. Okay. What I'm going to do now, I'm going to multiply each side of this equation by 3 to clear that fraction. We can do that to make the equation look nicer. Okay. By 3, what do we get on the left? On the left, we get 3y plus 6. On the right, we get negative x plus 1. Okay, and now they want us to put it in standard form. So let's move all x's and y's on the left side. So that will give us x plus 3y, and then the numbers without the variables, they can go on the right side. So that would be negative 6 from each side. 1 minus 6, that will give us negative 5. Okay, and that is your standard form, right? So to just kind of match it, okay, what is this? This is ax plus by is equal to c. Okay, so if you need to determine these coefficients, a is 1, b is 3, c is negative 5. Okay. All right. So once again, let me pause here for a moment. So take a look at problems 4 and 5. Take a little moment from writing it down, and let me know if you have any questions. And if not, just give me a thumbs up, your favorite emoji, whatever, anything, some sort of indication that you're on track with me.
Um, Real quick. So the ax plus by equals c that's the standard form, right?
That's correct. Yes. Let
Thank
me
you.
go back up here. Yeah, here we go. This is your standard form. Okay. And what's going to happen, this is, you don't need to know this for this class, but maybe some of you are interested. In calculus 3, we say, okay, how about this? Ax plus by plus c z is equal to d. Okay, so we just add that one more component, right? And now this is an equation of a plane in 3 space. Okay, so you will be revisiting this equation again, and that's one of the reasons why we start talking about it now. Okay. All right, let me go back to these problems here. So 4 and 5. Do you guys have any questions? Anything you would like to discuss?
I was gonna ask if it really matters what equation you do, because I kind of went ahead and worked on 4, and I used the slope-intercept, and I got the exact same answer.
Okay, no, it doesn't matter. I know what you did. So you use slope intercept to come up with this equation, right?
Yeah.
So how you start makes no difference. I mean, really, they're the same equations. All of these are equivalent. Okay, so if you feel more comfortable starting with the slope intercept form, that's fine. You can go ahead and do that. You will
Okay.
come up with exactly the same. Yep, very good. All right, let's go ahead and talk about a little bit about vertical and horizontal lines. Okay, what do they look like and what the equations are for those. Okay, so if I have a couple of horizontal lines, let's say I have this one right here, and let's have one negative, this one right here. So these are my horizontal lines. I know the slope here is 0, right? So slope is equal to 0. Again, interpretation here is this. As I'm moving along the x-axis, there's no change in the height, right? My line is completely flat. Okay, there is no change in my dependent variable in the function. Okay, what do the equations look like? The equations will be y is equal to a number, right? So y is equal to a number. All right, so in this one right here is y is equal to 3, okay? Constant, nothing changes here. The second line is y is equal to -2. And of course, it can be 0. Y is equal to 0. That's just your x-axis, right? Okay, where all coordinates for y are 0, you still have change in x. All right, so that's your horizontal lines. What about vertical lines? Vertical lines, let's have a couple. I'm gonna make them in purple, so let's do -4 here, and let's do 1. So I have 2 vertical lines, okay? Slope for those is undefined, right? So that's what that we already discussed. That it does not exist, undefined. Okay, what about the equations? Now, in this case, what is constant? If you look at that vertical line and look about all of the points and their coordinates on that line, all of the points will have the same x coordinate, right? Y's will vary from -infinity to infinity. So these will be x is equal to a number. All right, so we have x is equal to -4 here. And this one is x is equal to 1. And of course, x is equal to 0. Similarly, that's your y-axis. Okay? All right, and that's all we really need to know when it comes to vertical and horizontal lines. There is not much else to it. Okay, so let me go ahead and just project everything that we've done on this page, right? And just do a quick rundown. So we've discussed how to compute the slope, what it means, right? A couple of different ways to compute it. What we have as far as possibilities, greater than 0, less than 0, 0 and undefined. That's it. Nothing else can happen. And we've also come up with 3 forms of an equation, right? And when to use it. And somebody brought up that you could use slope-intercept form to solve one of the problems, and that works out well. Okay, so take a look at this page. Let me know if there's anything we should discuss before we move on. Everybody's good? Okay, then the next thing that we're going to do, talk about parallel and perpendicular lines. Okay, let me go ahead and do a side note here. So perpendicular, no, actually let's start with the parallel. Parallel lines, right? Okay, let's just have a quick picture of what those lines would look like. Okay, so let's say this one has slope m1 and this line has slope 2. What do you guys think the relation is between slopes for two parallel lines? Does anyone have a intuition that tells them? Yep, so Jeremy says they are equal. Yes, so m1 is equal to m2. Okay, you can think about these lines. They're changing in the same way, right? They have the same rate of change. They're shifted, so they might start at different points. Okay, they're shifted in the plane, but as far as the change goes, it's exactly the same. So parallel lines do have the same slope. Okay, so that's important for us to remember. And how about perpendicular? So what does that mean for two lines to be perpendicular? Okay, so what would be a picture here? Here's one line, and if they cross, they will form a right angle, right? These lines are perpendicular. So let's say this line has M1 and this line has M2 as their slopes. Okay, now let's just think about it from a logical point of view. One of these slopes is positive and the other one is negative, right? So positive times negative will give us a negative every time, no matter what those values are, right? Now, if we have two positive, that's fine, or two negative, that will also give us, the product will give us a positive. But in this case, one is positive, one is negative. So the product will be negative, but it's not even just that. If you do the product of two slopes for the lines that are perpendicular, we get -1. Okay, and this is how we're going to check if the lines are perpendicular. Okay, now if none of those conditions are satisfied, then the lines have different slopes and they intersect but not at a right angle. Okay, so now let's go ahead and take a look at this problem 7 and see if we can answer this question. Are they parallel, perpendicular, or neither? Okay. All right, I'll pick my first problem here. I'm going to rewrite both of these equations in the slope-intercept form. So my line number 1, if I solve for y, that's going to be 1/2 x, and then 10 divided by 2, that will be 5. Okay, and then line number 2, if I solve for y, it's once again is going to be 1/2 x. Now what is this? 4 divided by 2, that's 2. Okay, so before I even graph them, I can see that they do have the same slope. Okay, they have the same slope, 1/2. Okay, and do they have the same intercept? They do not. They have different intercept, right? So 5 for the first one, 2 for the second one. We can graph it. So how do we graph a line if we know their intercept and slope? Okay, so we start right here. That's my intercept, 5 for the y coordinate. What does the slope tell us? The slope is 1/2. That means if I go 2 units to the right, 1, 2, I also go 1 unit up. Okay, it's rise over run, right? Okay, that's my change here. So that is my first line right here. Okay, that's done. Same type of logic for the second line. Where's my intercept? This one is at 2. Slope says go 2 to the right, 1 up. We only need 2 points to grab these lines. Let me go ahead and label them. Okay, this is L1, this is L2. And you can see that even though our sketch is, by hand, right? It's not super accurate, but you can see, yeah, these two lines are indeed parallel. So parallel, we've confirmed it algebraically by determining what those slopes are, and also graphically. And of course, you can use Desmos to just check it again with a graphing utility. All right. So let me stop right here for a moment. Take a look at this example. Let me know if there is anything you would like to discuss before we keep going. What do you guys think? Is this brand new for some of you, or have you seen this before? Because a lot of you are coming from very different schools, right? So it is hard to know what exactly is the background. But could we talk about it just for like a minute? Is this something you're familiar with? Anyone?
I mean, kind of. I don't remember a lot of this stuff, but it does look familiar.
Okay, so if it feels like you've done it, but you just need a reminder, that's great. Okay, good. All right. Then let's go ahead and keep going we have 3 more problems to solve before we get into applications. Okay. Let's see this first one. Problem number 8. Find the equation of the line parallel to the given line. Okay, so parallel to this one. I'm highlighting the keywords and passing through the point A with coordinates 4, 5. Okay, so they want us to find an equation of a different line, right? This is a different line that's parallel to this one, and it also goes through this point. So there are some conditions here, right? So that we need to take care of. Okay, let's call this line L1. Okay, so the slope of L1, okay, can somebody tell me what that slope is? Just by looking at that equation. What is the slope of the line? 2. Okay, good. So that's from here, that's our slope, okay, which means the slope of our line that we want, let's call it M2, is also 2. Okay, I'm writing justification here because the lines are parallel, right? Okay, so we know that much. The line that we want to construct an equation of is parallel to this one. That slope is 2. And we have a point. Oh, we've got everything. We've got everything that we need to come up with an equation. So that would be y minus 5 is equal to slope is 2, x minus 4. Okay, again, let me label everything here. Here's my y coordinate, this is x coordinate, this is my slope 2, right? Okay, and now we can simplify this. So this is y minus 5 is equal to 2x minus 8. So if we write it in a slope intercept form, that's going to be 2x minus 5 minus 8 plus 5, right? So what is that? That's negative 3. And that's the equation that we would like. Okay, how would we check this? Let's see, I have 2 conditions. It needs to be parallel to that line. Is it? Let's see, the slopes are the same, so yes, it is parallel. It also needs to go through the point 4, 5. So if I plug in 4 for x, do I get 5? 2 times 4, it's 8 minus 3, that is 5. Okay, you could also check this graphically. So let's go ahead and do that. I'm going to go to my Desmos application. Okay. And type in my first line, as is, without changing anything. Y minus 3 is equal to 2 times x plus 7, right? So that's my original line. Okay. And now I'm going to type in my answer. What did we get? We got y is equal to 2x minus 3. Okay, I want to make sure that also my point is there. So 4 comma 5, I'm going to label it, and let's move it away, and there it is. So the red line is the one that's given to us in the problem. Okay, the blue line is the one that we found, and it satisfies the conditions that were given to us, right? So you can see they do not intercept, and that point that we picked is on the line. All right. So you can feel free to use this to just double check your work. And you know, if you feel comfortable with this material, of course you don't need to. But as we keep going, especially once we get to like exponential logarithmic functions, I strongly encourage you guys to just double check that what you have on your paper matches the graph, right? And that's how you kind of check your double check and triple check everything if you have to submit something. Okay. All right. So let's go back here. So we've checked this equation algebraically. We've checked it graphically. We're good to go. All right. Let's see. I'm gonna do problem 9 and 10, and then I'm gonna stop and collect any questions if there are any. All right. Let's see. What is the next problem? It says find the equation of the line that's perpendicular. I'm going to highlight keywords here. Perpendicular to 2x minus y is equal to 1. So that's my first line. Passing through the point B with coordinates negative 5, 2. Okay. All right. I'm going to take my first line and solve for y so I can see what that slope is. That's y is equal to 2x plus 1, right? Okay, that is my line. Nope, is it plus 1? That's negative 1, right? Should be negative. Here we go. So 2x minus 1, that's my first line. I want the line that I'm constructing to be perpendicular to this. So if the slope here is 2, what is M2? Somebody tell me? What do you guys think? Negative 1/2. Very good. So it's the number. It's a unique number. There is only one such thing, right? So that if I multiply 2 by, I'm going to get negative 1. So it needs to be negative, and you can think about it as negative reciprocal. That's all that is. Okay, flip that fraction, change the sign. Okay, that's our slope. Now let's go ahead and put this into the equation. So y minus 2 is equal to negative 1/2 times x minus negative 5. Okay, let's see, let's simplify this. This is y minus 2 is equal to what? Negative 1/2 x. And then here I have 3 negatives, right? Which will give me a negative. You can distribute that inside the parentheses first. You're going to get x plus 5. And then times another negative, we're going to get negative. So this will be minus 5 over 2. Okay. Let's see. What now? We need to just add 2 to each side. And we will get our slope intercept form. So this is negative 1/2 x. Negative 5 over 2 plus 2. So we get negative 1/2 here. Okay. And that is your answer. If it doesn't specify which form they would like the equation in, just pick it. whatever you want. So in this case, I picked slope intercept. All right. So I have a line that's going down. Okay. And the y-intercept is at -1/2. Okay. Of course, you can check with Desmos to see if that is true. Let's go ahead and do that real quick. You go back to Desmos. I'm going to delete these graphs right here. So what is the equation of my original equation, my original line? So that would be 2x minus y is equal to 1. Okay, and a nice thing about Desmos, you can type in an equation in any way. When in the calculator, you have to type it in as y is equal to something, right? So you don't have to worry about it with Desmos. Just type it in just as is. Okay, so we have that that equation right here, and then we've come up with the following function: y is equal to negative 0.5x plus, nope, that was minus 1/2, so that's 0.5. Oops. Okay, I shouldn't have done it because now it's skewed, but it is. Let me make sure, yeah, I go back. Here we go. It is perpendicular. These two are forming a right angle. And you can also check if your point is there. What was that point? -5, 2. Okay, so -5 for x, 2 for y. There it is. Let's label it. Okay, and now we can see that we've done everything correctly. Okay, point is there. The lines cross at the right angle. We're good to go. Okay, so that's problem 9. Last one. This one is just extended one additional step. It says find the equation of the line in standard form. Okay, so they want a specific form. Perpendicular to y is equal to -3x plus 5, passing through C. Okay, so I'm highlighting all of the relevant information. Okay, standard form. So that's going to be the last step. All the previous steps are exactly like what we've done in problem 9. Okay, so my line here has the slope of -3. So what is the slope of the line that we're trying to figure out? Somebody wants to tell me? Let's see, Haley says 1/3, very good. Flip that number, right? Okay, and change the sign to the negative. So negative of negative is positive, so that would be 1/3. We have a point. Here we go. So now we just need to put it into the equation. Y minus -1 is equal to 1/3 times x minus 6. Okay, that's our setup. Now let's go ahead and simplify this. So this is y plus 1, 1/3 x minus 2. Okay, let's see. I'm going to move all my variables on one side. So that's going to be y minus 1/3 x. And what's going to happen to the coefficient on the right? So that's -2 minus 1. That's going to be -3. Okay. Now it is common to have these coefficients as integers, so whole numbers. So I'm going to multiply everything by 3 to clear that one fraction that we have. So I'm going to get 3y minus x is equal to -9. Okay, you can keep it as is. If you feel like rewriting it with x first, that's fine too. And some of you would probably prefer negative, and positive x. That's also okay. So just make sure you change the signs for all of them. This becomes positive 9. So all of these are okay. So this one is fine, this one is fine, this one is fine. I'm not really picky when it comes to this, as long as they are consistent, right? So as long as they're mathematically correct. All right, so this is it. That's your standard form of the equation that we're trying to figure out. Okay, let's go ahead and check it. So we've done it for the previous problem. So let's go ahead and do the same thing here. Let's see, y is equal to negative 3x plus 5. That's my first equation. Y is equal to negative 3x plus 5. Okay, and what was my equation? Which one do I want to use? Let's do x minus 3y is equal to 9. X minus 3y is equal to 9. Okay, what was the point that we were using? Let's see, it was 6, negative 1, right? 6, comma, negative 1. There it is. Okay, the two lines cross at a right angle. They are perpendicular, and the point is on that green line. Okay, so that's a good way to check if you're doing it right. Okay, let me go back to these problems, project the whole thing. Okay, let's go ahead and take a moment, review all of the solutions. Let me know if you would like to discuss anything. And then once we do the discussion, we'll take a quick break, just like we did on Monday.
I just wanted to clarify real quick. For number 9, when you added 2 to the negative 5 halves, you're really adding 4 over 2 to the negative 5 halves, right?
Correct. So that's one way to think about it. I also kind of think about it as I have negative 2.5 and then a positive 2. So I'm left with just negative 1/2. But it's identical. I mean, it is exactly the same.
Okay.
Yeah, so however you feel, this is what we call a number sense. How do you feel about numbers, right? So and they're really all equivalent ways to think about it. But if you would like to convert it into a fraction, that's completely fine. That's good too. So you converted the 2 into a fraction, 4 over 2, right?
Yeah.
Yeah, and if that's how you think, that's great because it's correct. Okay, I kind of thought about it in a slightly different way. I was like, okay, I have a positive 2 and a negative 2.5. So in absolute value, my negative number is bigger. So when I add them all together, I have more of the negative value. Does that make sense what I'm saying?
Yeah.
Yeah, it's kind of like I have $2 and somebody asked me for $2.50, right? And then now I'm half a dollar in debt, kind of thing. Okay. Let's see. I have another question for number 2. Would you have to clear the fraction at the end, or would it be marked off? Okay. So I wouldn't mark it off. No, no, no. So if mathematically the first one right there with the fraction, that is correct. It is a standard thing in mathematics, and honestly, I don't know why, that we want to do integers. It's not incorrect to leave it with fraction, and if you're good with fractions, then that's fine, unless there are instructions on homework. So sometimes they will say, make sure your coefficients are integers. Then yes, then you would need to clear the fractions. Okay, does that make sense, Jeremy? Yes? Okay. Let's see. Thomas, I see you raising your hand. Go ahead. What is your question?
Yeah. So for number 10, what happens to the -2 on the end? Like, where does
Oh,
that
okay.
go?
So -2 becomes -3, right? Because I'm going to subtract -1 from each side. Is this the step that you're missing, maybe?
Yeah, sorry.
So yeah,
So
1 minus 1, that's 0 on that side. That's okay. And then negative 2 minus 1, that's where this negative 3 comes from.
thank you.
Yes. So you guys, I just want to give you a little bit of kind of heads up of that is we're working through these topics, right? If you feel like you missed a step, or I'm I skipped a step, because sometimes that happens, right? Don't hesitate to tell me, um, because I feel really comfortable with this material. You don't have to. This is why you're here in this class, right? And then if I'm going too fast, you go ahead and tell me, okay, could you please slow down? What is the step here? All right. Because again, a lot of you coming from such various backgrounds, it's difficult to just do it, uniformly for everybody. So I'm trying to go as slow as possible, but again, I could be completely off and just going too fast. This is when you say, excuse me, please push those brakes. Okay, we got to slow down a little bit, and this is the step that I want you to go over, and I'll be happy to do it. Okay, I want to make sure that as you're watching these lectures, um, there are no gaps whatsoever. Okay, that everything is covered. Okay, I see a hand from Elijah. Go ahead, Elijah.
Um, for Newton, is this in
Hmm.
section 2.2, part 1, or is it part 2, or is it
This is
2.3?
part two. This is
Okay,
part two. Yes.
sweet,
So
thank you.
that would be the second part of Newton also. The first one is talking about solving equations, and then just like what we've done with linear equations and rational, and then the second one is about lines, constructing lines.
And
Okay.
and for the homework, so you were talking about us getting done section 2.2, part 1 and 2, and then 2.3 as well, right?
Yes. Yes.
Okay.
Yeah, so 2.3 will be applications, so word problems. We haven't done it yet, so we're gonna do it now. Well, not necessarily right this minute, but once I answer all the questions, I'm gonna let you guys take a little break, kind of stretch out, walk around, maybe grab some drink, and then we'll do that. Okay. All right. Let's see. Anything else? This is great, by the way. This is the most active I've had a class asking questions. I love it. I've been teaching structured remote for 2 years. And maybe because I've been teaching like a higher level classes, students rarely ask any question. It was just basically me talking the whole time. So I encourage you ask questions and participate. I love it. This makes it so much more enjoyable when I hear you and I kind of get that feel that you guys are actually learning. Because if you ask questions, that means you're thinking and you're processing this information. So thank you all for this really, really wonderful participation. Okay, so we're going to take a quick break because sitting in your chair for 1 hour and a half, or what is it, 1 hour 40 minutes is not healthy. Uh, let's go ahead and take a break for 5 minutes. So we will return around 11:58. Okay, I'm gonna go ahead and mute my microphone, but I will keep the notes loaded here. Okay. Let's see. I have a question. When is the deadline for the homework? Every Sunday. So that's one way to remember. All of the homework for that week is going to be due on Sunday. And as I mentioned before, you can you guys hear me at all? Sometimes my
Yes.
mic doesn't. Okay. You can ask for extensions. That's fine. But every Sunday, whatever we cover that week, that homework is due.
I forgot if you said this last meeting, but do you record your meetings and put them on Blackboard or no?
Yes, it's already
Okay.
there, right? Were you guys able to see it? So if you go to week one, so unit one, week one, one of the folders says remote session one, January 24th, 2022.
Yeah,
The
I see it. I
lecture
see it.
notes.
My
Yep.
bad.
Yeah, that's fine.
I was just
So
asking because I actually have to leave soon in like 12:30.
that's fine. No worries. We might be done by then, actually.
All
We
right.
only have 4 or 5 problems to solve. Okay. But yeah, if you have to miss the remote sessions, those are recorded. And it takes some time for the videos to get put on Blackboard, but the notes will be almost right away. Just takes me a couple of clicks to email it and upload it. Okay. All right, 12 o'clock. So we have covered the first 2 sections of this chapter. And in this section right here, 2.3, we will talk about models and applications. And here we will basically use linear functions. So that's the form y is equal to mx plus b, okay, to model situations. And you'll see that some of these problems will be financially related, others will be distance. This is a very popular topic to address when it comes to modeling. Then you'll see some geometry, but in general, many different things can be modeled with applications. Now, having said that, in real life, the models are a lot more complicated than what we're doing here. So one of the goals of this chapter is to just learn this process of creating a function that models this behavior. Okay, you might be saying, well, is this situation realistic? Probably not. Most of these are, you would never really do this in your future career. But the process of reading this information, extracting important parts, and putting into the equation, that's one of the main focuses that I want to emphasize. Okay, so we have, let's see how many, 5 problems to go through. Okay, and we're going to use a line to model all of these. So let's take a look at the first one. This one is a distance problem. We have the following situation. After 2 minutes, we have an ant that traveled 100 meters. And then after 6 minutes, that ant traveled 220 meters. So that's our scenario. And we're asked to answer these questions A through D. Okay. The first one says use a linear equation to model the distance traveled by the ant. So distance traveled will be our dependent variable, right? So distance depends on time. So we have distance in meters, time in minutes, okay? You can keep the same variables at y and x, or you can introduce new ones, whatever you would like. I'm gonna go ahead and introduce the new variables. So d is going to be my distance traveled, and then t, that's going to be time. So d depends on t. Okay, you can think about d, that's your y, t is your x. So the first thing that we need to decide is how we're going to create that model. Now remember, to come up with an equation of a line, we need point and intercept. I'm sorry, point and slope, right? Okay, we don't actually need an intercept. Any point and the slope. Well, we have 2 points. What are our points? Our ordered pairs here are 2 100 is my first point. My second point is 6, 220. So I have 2 points that are not explicitly given to me as an ordered pair. So that's my job to just kind of put it in this form. Familiar, right? From here, we can find the slope. Okay. So what is the slope? 220 minus 100 on top. That's the change in my dependent variable over 6 minus 2. That's 120 over 4, 30. Okay, that is my first step here. I found the slope. Now we need to find the intercept, right? Okay, if we want to put it in the slope intercept form. So I'm going to use the equation that we have used before, point slope, and you can use either one of these points, either 100 or 6, 220. Okay, I'm going to go with the first one, smaller numbers. So this is going to be y minus 100 is equal to 30 times x minus 2. Okay, so from here, we go into, well, let me go ahead and just do all of the steps. So this is going to be y minus 100 is equal to 30x minus 60, right? Now I'm going to add 100 to each side. So I end up with y is equal to 30x plus 40. Okay, that's my equation. Let me go ahead and write it here by that's the answer. Y is equal to 30x plus 40. Okay, you can also check and plug in those ordered pairs to see if we get the correct answer. Okay, if it matches the equation, you'll see that it's going to work. All right, so that part is done. Explain the significance of the slope. This is how your function changes, right? So this one would be just a sentence in words, in plain words. We would say the following, okay? S, the ant travels for 1 unit of time, right? For 1 minute, okay? Or for each 1 minute traveled. The ant travels for 1 minute. The distance traveled increases by 30, right? That's what the interpretation is. Okay. As we go 1 unit to the right, okay, we go 3 units up. But in the context of the problem, as we move for 1 minute, the distance traveled goes up by 30. Why does it show that it's 3? It should be 30. 30. Okay, that's your explanation in simple words, right? That's what the slope is. The next part says predict the distance that the ant will travel after 12 minutes. Okay, so now let's think about it. What is that 12? 12 is time. That's our independent variable. So all I need to do is plug in 12 for x. Okay, so that would be 300 times 12, which is 360 plus 40, that's 400. So after 12 minutes, the ant would have traveled 400 meters. Okay, so here we used the information that's given to us to answer the question, but we have to be careful. What is that 12? What does that go? That goes for the independent variable. That's my time. Okay, and then, oh, I never rewrote it in that form. Well, I'll come back to it and rewrite it in the one notation that I came up with at the beginning. What about the last part? Determine the number of minutes it will take the ant to travel 400 meters. So now this is distance, right? Okay, so 450 goes here for y, and then here we have 30 times x. X is the unknown now, right? Plus 40. Okay, so subtract 40 from each side. That's going to be 410 equals to 30x. Here, x is equal to 410 divided by 30, which doesn't divide nicely, so that's roughly 13.6. That 6 is repeated. Okay, that's in time, so that's in minutes. That's our time. The answer in part C, that's 400 meters. Okay, so we've done everything. So if I were to use my notation, what would the formula look like? It would look like distance is equal to 30 times t plus 400 plus 40, not 400, plus 40. So but it doesn't really matter. No, not really. I just want you to know that sometimes when you'll see examples worked out, they will use slightly different notation just to kind of match the words, and it doesn't always have to be x and y, right? It can be really anything. Okay, all right, so let me pause right here. You guys take a look at this solution. Let me know if there's anything you would like to discuss.
Yeah. One question. For the distance traveled, what is the base formula for that?
So distance travel is a function of speed and time. Is that what you're
Okay.
asking? Yeah?
Yeah.
Okay, so distance would be then speed times time traveled, right? Okay, and that's actually what we're going to use in the next problem. So that will come in handy. Speed times time. All right. Anything else you guys would like to discuss before we take a look at that next problem? All good? Okay, then let's go ahead and take a look at this problem. This one will be a little bit more involved. You'll see what I mean by that. So let's read this. We have Stacy who starts riding her bike at 20 miles per hour. So she rides that for a certain amount of time. Then after a while, she slows down and her speed becomes 12 miles per hour. And then she maintains this speed for the rest of her trip. The whole trip distance is given to us. Okay, it's 70 miles. And also the entire time is given to us, 4.5 hours. Okay, the question is, for what distance did she travel at 20 miles per hour? So what is that first chunk? How long was that? Okay, so this is a problem that I think is important to have a picture here, just to kind of break it down and see what is it that we're really trying to find. Okay, so I know she traveled 70 miles total. Okay, so let me make that picture here. That whole distance is 70 miles from 0 to 70, right? Okay, that's my total distance. Now, she traveled part of it with one speed and then the other with a slower speed, right? So let's just kind of break it down anywhere. We don't know which part is bigger, which one is smaller. So somewhere here, okay, this is the part that she traveled with speed number 1, which was 20 miles per hour, and this one was 12 miles per hour. Okay, we would like to find how long she was going for 20 miles per hour. Okay, what is this distance right here? Okay. Now, if we find what the other piece is, we can also just subtract it from 70, right? So, but that's all of the information we have. And we also have that the total time it took was 4.5 hours. Okay. So how are we going to approach this problem? Okay. So we'll start with with basics. What do we know as far as the relations go between distance, time, and speed? Okay, and that was already brought up. So distance is equal to, that's our general formula. Distance is equal to speed times time. Okay, so one way to approach it, okay, is come up with the variable that we would like to find out, right? So we want to know what that distance is for for the length that she traveled with 20 miles per hour. Okay, that's going to be my unknown. So I'm going to say x is the distance traveled with speed of 20 miles per hour. Okay, so then what is the distance traveled with the slower speed, with the lower speed? What is it? Can anyone get an idea? If x is how long she traveled with 20 miles per hour. Okay, so somebody says y. I want to have it in terms of x. See if you have a good idea. If not, of course I'm going to tell you. So x2. Is it x2? Is that what you're saying, Elijah? Yeah, okay. So I think I know what the confusion is. Okay. So I'm just gonna go ahead and guide you through it. If x is the distance traveled with speed of 20 miles per hour, then the other distance, this one right here, the one I'm gonna highlight in red, is going to be 70 minus x. Okay, do you guys see that? Is this step right here, is this clear? Because this one is important, right? So let's just say, let's do this quick exercise. Let's say I traveled with that first speed for 10 miles, right? For 10 miles. How long did I travel with the second speed? And the total travel distance was 70. So if I traveled for 10 miles, how long did I travel with the second speed? So I'm Stacy now. Don't overthink it. It's that easy.
60.
60, yes. It's 70 minus 10, right? So if I tell you I traveled for 45 miles with the speed of 20, how long did I travel for with the other speed? What's the answer? So 45. Yeah, Jeremy, how did you get that 25? You're right.
Just
Correct.
subtracted it from 70 or 45 from 70.
Good. Now let me go ahead and put it this way. I traveled for X miles with the speed of 20. How long did I travel the other part? It's in the notes. I traveled X, right? So I traveled X miles with the speed of 20. How long did I travel? The other part with the other speed with. It's 70 minus X, right?
Yeah, the
So
remaining minus, yeah.
yes, it's going to be exactly the same. So what we built in here is a model, right? So you define one variable that's unknown and see if you can make a relation with everything else with that variable. That's it. This is the one we picked. Okay. Setting up substitution, basically, yes. So that's one way to think about it. Okay. So now that we have these two distances set up with one variable, you see, like if you set it up as y, that's fine as long as you also define what that y is, right? Y would be 70 minus x, okay? So that's just one intermediate step. So we have the distance for first speed, we have the distance for the second speed, okay? Now we know the total time traveled. The total time traveled, so let's say Stacy traveled for some portion of the time here, T1, and also T2. And we know that if we add them up, right, T1 plus T2, that will give us 4.5, okay? We know that if we add up those times separately, yeah, so if we know how long she traveled with this speed and how long she traveled with the other, we add them up, we get the total time. So now this gives us an idea of how to set up our equation. So T1, okay, how long did she travel with the speed of 20 miles per hour? So it would be distance 1 divided by the speed 1. Distance 1 is x, speed 1 is 20. Okay. Second part, how long did she travel with the speed of 12 miles per hour? What is the distance there? The distance is, oops, yep, 70 minus x. What about speed? That's 12. Okay. So where does this come from? That comes from this formula right here, right? If I were to solve for time, it's distance divided by speed. Okay. So now I can put it all together. This is x over 20 plus 70 minus x over 12. And that's equal to 4.5, right? So I'm going to rewrite this. No, and actually, I'm going to be fine with if I just write it with a decimal. It's 4.5. Okay, that's the fundamental equation now that we need to solve here. Okay, it's a linear equation in one variable, right? We want to have one variable. We've done it last week. We know how to solve this kind of problem. Okay, once we set this up, that's half the battle. And that's typically the difficult part, setting it up. All right. So now what am I doing here? I'm looking at these numbers in the denominator, 20 and 12. I'd like to find a least common multiple, right? So this would be what? Let's see. 12 doesn't go into 20. 12 doesn't go into 40, and Jeremy says 60. Yes, so we're going to multiply each side by 60 to clear our fractions. And then 60 on the right. Okay, so let me put my solutions here. Let's see, 60 over 20, that will give us 3x, right? Okay, 60 over 12, that's 5. So 5 times 70 minus x. And then here, 60 times 4.5. You can use a calculator for this one. You will get 270. Okay, so now let's multiply everything through, combine like terms, and then solve for x. 3x plus, what's 5 times 7? That's 350 minus 5x. That's equal to 270. Okay, I'm going to move all the numbers on the right. So let's see, 350 minus 270. And then 3x minus 5x, that's negative 2. So it will be positive 2 on this side. So that gives us 80. Oops, x on the other side. 80 is equal to 2x. X is equal to 40. Let's go back here. What was that? 40 was this distance right here, D1. Let's call it D1 is 40. Okay, so she traveled 40 miles with the speed of what? 20 miles per hour. Okay. All right. Let's see. What does it mean? What was the distance that she traveled with speed 12 miles per hour?
30.
Yep. So D2 would be 30. Okay. And that one is just 70 minus 40. All right. And you can answer more questions about it. You can answer questions like, how long did she travel with the speed of 20 miles per hour? How long did she travel with the speed of 12 miles per hour, and so forth. But in this case, we're only asked to do 40. So this is it. That's your answer. The answer is 40 miles. Okay. All right. Let me stop here for a moment. What do you guys think? Any questions here?
I kind of did something different.
Did you get the same answer?
Yeah.
Excellent. That's the beauty of math. You can you can solve a problem in multiple ways and still come up with the same answer. That's what we call consistency. Okay, otherwise we would have some issues if we were doing the right thing in two different ways and get different answers, right? Okay, what did you do?
So I was kind of looking at it as 4.5 hours, and I
Yeah?
kind of figured that there would at least be 40 on the 20 miles an hour thing. And then I did 12 times 2, and I took that half of 12 for the other one, giving me 30, and 40 plus 30 is 70.
Okay, so you kind of did an educated guess, right? Like there's no like a rigorous solution there.
No, I was
Is
just
there?
kind of looking at it and trying to see how it would add up evenly.
Yeah, I mean, okay, yeah, so this is fine. This is a logical way to approach it. And mine is a little bit more rigorous, right? So that kind of breaks everything down and leaves nothing to question. Okay. But all right, so that works too. Very good. Let's see. Any other comments or feedback?
I have a question. When you
Yeah.
did the 60 and you multiplied it by the equation, how does
Mhm.
60 times 70 minus x over 12 get you 5 times 70 minus x?
Okay, so 60 times this, right? How many
Oh,
times yeah, so 60 divided by 12.
okay. Sorry. Thank you.
Yeah, you're fine. You're good. Again, so some of these steps I'm skipping because they're obvious to me, but they might not be obvious to you, which is completely fine. And this is when you do what you do, right? You ask questions and say what's happening here. Okay? Yes, so I'm reducing this in my head. Okay? But you can take that extra step and write it out. All right?
Okay. Thank you.
Yeah, sure. Okay, if there are no questions, let's go ahead and finish the last three problems. Well, we're gonna have time. Yeah, we should be okay. The last two, these problem 3 and 4 are not too complicated, and problem 5 is also pretty simple. Just a little bit new notation here. So these are geometry problems. The first one says find the dimension of a rectangle. Given that, this should be that. The parameter is 110 inches, and the length is one more than twice the width. Okay, so I have a rectangle here. The parameter, we know it's the sum of all length, right? So let's say if this is y and this is x, then it's 2x plus 2y. Okay, that's my parameter. No, I don't want to paste anything here. And then what else do they say? The length is one more than twice the width. So you would say y is equal to 2x plus 1. We're converting this expression in simple words into a mathematical equation, right? So y is one more than twice the width. Okay? This is equal to 110. So now this is a straightforward substitution here. we can reduce the equation for parameter to just have x plus y is equal to 55. We can reduce that equation by 2, just divide everything by 2. And now we're going to substitute this expression for y because we have y in terms of x. So that gives us x plus 2x plus 1 is equal to 55. Okay, and that's a simple equation to solve. This is 3x is equal to what? 55 minus 1, that's 54. Nicely divisible. 54 divided by 3. What is that? It's 54 divided by 3. Did I do that? Let me
18.
see. 18. Okay, so x is 18. Thank you. All right, so that's my x. What about y? Y is twice that. That's 36 plus 1. So that's 37. Let me make sure I'm consistent. So this will be 18 by 37. All right. So this one is a little bit more straightforward than the one we've done above, right? Okay, you know the formula for the parameter, and we transform that expression in English into a mathematical equation. Okay, we can extend it a little bit more. So a similar idea here, I have a garden with the parameter 80. It's going to stay with the same notation here. So 2x plus 2y is equal to 80. Okay, what's the relation that they give us? The length is 5 more than twice the width. Can somebody give me that relation in a mathematical form? You guys have a good idea what that means? What is the relation if we would describe it as the length is 5 more than twice the width? Okay, I see Jeremy is typing y is equal to 2x plus 5. Very good. So this is y is equal to 2x plus 5. Okay. Now they want us to find the area, right? So just one more step that we need to do here. Okay. Let's go ahead and reduce this equation by 2. Okay. And now we're going to substitute it. X plus 2x plus 5 is equal to 40. Okay, we will not get nice numbers here. We'll get fractions, but that's all right. So 3x is equal to what? 40 minus 5. That's 35. That's not divisible by 3. That's okay. You can just keep it as is. 35 over 3. That's my x. What about y? So y would be 2 times 35 over 3 plus 5. Okay, so what do I have here? 2 times 35, that's 70 over 3. So I'm going to do this actually if I were to do it by hand, right? And then if I do 3 here in the denominator, then what goes in the numerator? That would be 15, right? Okay, so this is 85 over 3. Again, this is not divisible by 3. You're going to get a repeated number, and that's okay. But that is my y. So then what is the area of this rectangle? Do you guys remember the area formula? It's pretty straightforward. We have width and length of a rectangle. Yeah, it's x times y. Very good. So we will do 35 over 3 times 85 over 3. And of course, I'm not going to ask you to do this by hand. You could use a calculator to get approximated answer, right? So 330.5 repeated, and that's your area. Now, our area is going to be in square units, right? Whatever these units might be. Oh, that's feet. Okay, so let me go ahead and change that to square feet. Okay. All right, let me pause here for a moment. Take a look at these two geometry problems. Let me know if you would like to discuss anything before we finish our last problem for this lecture.
My only question is like, am I able to like pull these formulas up on like the textbook? I like to write them down for notes.
They are in the textbook. And for the exams, you could use like a formula sheet. That's what I'm gonna let you guys have it. So you can write whatever you want in the formula sheet. Um, it is kind of assumed that we remember fundamental formulas such as, you know, a parameter, area, but typically in the actual book, they're mentioned at least. Okay. Now, if there's something that you're struggling to remember, you can always just ask. I don't mind. I'll tell you what that is. Let's say a formula for the area of a circle, right? It's pi r squared. Is it expected that we remember this? Yes, to be honest, yes, but it's not a big deal if you don't. You can look it up and just kind of keep in mind that Euclidean geometry basic formulas, yeah, we kind of assume that we know them. Okay, if that's something that you need to put on a formula sheet, go for it. Absolutely.
Yeah, I think I'm following along with all of the uh, solutions and kind of how you're solving it. It just, I think some of the starting out basic formulas, I just need to go back through and remember. That's all.
Yeah, and it will come back. It will come back. Like some of these things that you're like, oh my God, yes, we've done that like 5 years ago, right? So they will return. Um, and again, like as you guys are prepping for exams, you can make those formula sheets and but don't stress out about it too much. If I think that you need to know a specific formula and it's unreasonable for me to assume you know it, I'll just tell you. I'll just put it on the actual on the actual exam and say, by the way, this is the formula that you would use. Okay. All right.
How
Last
did
one. Yeah. Oh, go ahead. Go ahead. Go ahead. Sorry.
how did you get 15 over 3 for the area one or for the y one? I mean,
So let me highlight this part right here.
yeah.
Okay. So this is going back to basic, right? 5/1 is equal to, if I put 3 on the bottom, then it's 5 times 3, right?
Uh,
So I just found a common denominator, right? So the common denominator is 3.
so
And
you
you
don't
can also,
multiply divide by 2, you multiply it by 3 because that's the denominator you're getting.
correct. So I'm not multiplying it by 2 because the formula that I'm matching it is this one, right? It's 2x plus 5. That's my relation between the two lines, right?
Yeah.
Okay. So it's not 2 times x plus 5, quantity x plus 5, right? It's just 2 times x. We found x right here. And then 5 is separate. And then I multiply 2 times 35. That's where that 70 comes from. But I'm also seeing, oh, I have a fraction there. So I want to rewrite 5 as a fraction with the 3 in the denominator. Does that make sense?
Yeah.
Okay, good.
Thank you.
Yeah. All right, let's see. Let's go ahead and finish this last problem. I know we only have 3 minutes to go, but I want to have this completion for the week. Okay, we have a salesman that earns his salary in the following way. There is a stable amount of money, right? $2,250, and then commissions based on how much he sells. Okay, how much product he sells. So we have 5% commission if his total sales under $10,000, and then the commissions increase as his sales increase. And this makes sense since we want to encourage, right? So we want to encourage higher sales. So that's his motivation, right? He will earn more if his total sales are higher. Okay, so here you have a lot of information and a lot of numbers, but the solution is actually pretty simple. It says write 3 separate linear equations representing the salesman's monthly wage in terms of the monthly sales. Okay, so I am going to use different notation here. So S is going to be the salary, and then let's see, X is going to be sales. Okay, his personal sales, how much he's done. So S as a function of X. Okay, 3 scenarios that can happen. Okay, let's say he sells under $10,000. Then he still gets 2250 plus 5% of whatever he sold. Okay, that's 0.05 times X. X represents the amount that this person sold. Okay, and that's if X is less than $10,000. That's my condition here. Okay, let's see. What if he sells more than that? Then he still gets that base amount plus 0.10. That's how we compute the portion, right? That's 10% of X. What is my condition here? It's this one right here. So this is if our value for X is between, I'm going to abbreviate it with K because I'm running out of space here. And then less than or equal to 14. Oh, okay, here I have to go with this 14,999. Okay, this is all in dollars. And then the last part would be if he sold more than that. Still, the base amount is the same, 2250 plus, what does he get? 12%. So that's going to be 0.2x. Okay, if his sales are between 15K and looks like 17,999, so just under $18,000. Okay, so what we're introducing here is your first view of a piecewise defined function. Okay, we have slightly different equations depending on what the conditions are for X. Okay, so now I'm going to speed it up because I don't want to hold you guys too long here. Determine the monthly salary if he sold 1650. Okay, that's how much he sold in March. I'm going to look at my conditions and see where that number falls. This is the amount of sales. It falls into this interval, right? It's between 15 and just about under 19. Okay, I'm sorry, 18. So that's what I'm going to plug in. So for the month of March, his total salary is 2250. He gets that amount regardless, plus 12% of his entire sales. Okay, and that's that. So I'm going to use your calculator to compute this value. We're going to get $4,230. Okay, and now you can see that if your value was, let's say, $9,000 in sales, you would put it in the first equation. If you have something like $12,000, you would put in the second equation. Okay, all right, I'm going to stop the recording right here, but I'm not leaving. If you guys have any questions, you can stick around, but let me go ahead and stop the session now.